So we know that power is equal to the change in energy over time. When we're dealing with electricity specifically, we can change this equation to be a little bit more useful to us. For example, we know that when we're dealing with electrical energy, we have this relationship, or I should say we have this definition of electric potential difference. Electric potential difference is equal to the electrical energy over the charge. So one thing we can do is if we solve for electrical energy, E equals V times Q, we can replace that in this equation for power. V times Q over T, right? So it's the electric potential times the charge over time. We also have a definition for current, which equals charge per time. That might look a little bit similar to what's over here, charge per time. So we can actually do a direct substitution of I instead of Q over T. And it's going to simplify this a lot. So the power, in other words, is equal to the electric potential difference times the current. This is useful because we don't need to worry about time or energy in order to find power. If we know the voltage of a circuit and we know its current, we can easily find the power like that. There actually are a few other equations. There's two other equations that can be derived in the same way, and they make use of Ohm's law. We know Ohm's law is resistance equals voltage over current, right? So if we replace these things with these things in here, we can get three equations total that are going to be very useful to us. I'll let you derive them as an exercise to yourself, but the three equations, and they appear on your formula sheet, are P equals V times I, or I times V, usually we see it as I times V. So power equals current times voltage. Power also equals current squared times resistance, or power equals voltage squared, or potential difference squared, over resistance. And again, these both come out of just replacing these variables in using Ohm's law. So I'll let you figure out how to get those. Keep in mind, when we're doing this, power is measured in what? Watts. Current is measured in amps. Volts or potential difference, I should say, are measured in volts. Resistance is measured in ohms. So as long as we use these as our units when we plug stuff into the equations, we should be okay, right? So looking at our first example here, we notice it's a bulb that uses 7 watts of power, right? So power equals 7 watts. And we want to find the energy, so delta E is our question mark, that's what we don't know. Calculate the energy it needs to provide light for 24 hours. Well, you know that that's time, right? So in this case, are these three equations actually going to help us out? The answer is no, right? But we do know time and energy, time over energy is what power, the definition of power is, right? It's just energy divided by time. So we can go back to our regular definition of power. That still works for electrical energy, of course, because that's how power is defined. So power is, and in this case, we're trying to solve for energy, right? So let's write out the equation. Power equals energy over time. And if we're trying to find energy, it's just going to be power times time, right? Now, because we're working with a long period of time, specifically 24 hours, it might make sense to put our answer in kilowatt hours, right? And you'll see that's actually what the answer here is listed as, kilowatt hours. So in order to do kilowatt hours, remember we just need to put our units in kilowatts and hours. So power is 7 watts, which is if we divide by 1,000, 0.007 kilowatts, right? So 0.007 kilowatts times 24 hours, which gives us 0.007 times 24, 0.168, or rounded to two significant digits, 0.17 kilowatt hours. So that makes sense. but we didn't get to use those fancy equations on top. Let's see if the next one we have to do that. So a heating element of a stove provides or operates at 240 volts. This is common for a stove to operate at a higher voltage than the rest of the appliances, because anything involving heating requires a lot of power. So anyways, 240 volts, that's our electric potential difference, is 240 volts. We want to know how much electric energy is converted if it takes 5.5 minutes, so our delta T is going to be 5.5 minutes to bring a pot of water to a boil, drawing a current of 6.25 amps. So our current is 6.25 amps. Now, we're looking for energy, right? Delta E, once again, is our unknown, right? We have a few different things. How can we go about doing this? Well, it would be useful, I think, if we knew the power that the stove consumed, right? How many watts it consumes. Because if we know that, we know that energy is just power times time, right? So we can find our answer. So we luckily have those three equations, right? One of these can probably help us out to figure out what the power is. So if we look, the first one here has I and V in it, which is going to help us find the power. So that's the one we're going to use. We can't really use this one or this one because we don't have resistance, right? If we had resistance, we could use one of those other ones. This is sort of similar to those 5 equations of motion, where you have to sort of pick out the right equation that works depending on what you have. In this case, there's only 3 equations and 4 unknowns we have to take care of. But you got to still figure out which one to use. So in this case, we're using the first one, which is P equals I times V. It's a very useful equation. So power equals 6.25 amps times 240 volts. And if we use our base units, we're going to get out watts. So 6.25 times 240 gives us a 1500 watt stove. So that's basically how many joules per second it uses, right? It uses 1500 joules per second. So now if we want to calculate energy, we know that that equals power times time, right? And remember, watts is joules per second, so if we have 1500 joules per second, we want to multiply by units of seconds, right? So 5.5 minutes, if we multiply that by 60, we're going to get 330 seconds. So let's do that, 330 seconds. Those seconds are going to cancel out. 1500 times 330 is, that's a lot. 495,000 joules. That agrees with the answer here. We could actually write this to make it a little bit easier as 495 kilojoules, right? Also, if we wanted to, we could write this in kilowatt hours, right? So delta E is equal to P times T. And if we want to do in kilowatt hours, 1,500 watts is just 1.5 kilowatts. And if we wanted to convert 5.5 minutes to hours, we can just divide by 60. 5.5 divided by 60 is, well, I'm just going to leave it as 5.5 divided by 60 because it's not a whole number. So 5.5 times 60, this is how many hours it is, right? So we multiply by 5.5 and then divide by 60. So if we do that calculation, it's 1.5 times 5.5 divided by 60, which comes out to 0.14, if we round to 2 significant figures, kilowatt hours. So there we go. I would accept either answer in this case. A little bit less convenient because our time was in minutes, so less convenient to convert it to kilowatt hours, but it's essentially the same amount of work to do this one or this one, because this one we had to convert to seconds, this one we had to convert to hours. So those are both okay answers. So here are some practice problems. Give them a shot. The answers are there. See if you can come up with the correct answers.